I have something really cool to show off today. You'll get to see how I write code to translate voxel data into 3D mesh that could be used in a 3D program, for example, in a game that I'm making. All this is done in less than 200 lines of code. Let's begin with an explanation why I even bothered to write this. I'm making a game called Lizard with voxel-styled graphic, and a while ago I've bought a library to rig and import those models in Unity3d game engine. I've tried to use the library, but it was bad beyond repair. Code was buggy, extremely long and unclean. I originally planned just to rip out the unnecessary junk, but I couldn't just stomach it. After 3 days of suffering, I've decided to write my own library for this purpose. I'm doing it totally from scratch. Ultimate goal is to just select a file and get rigged model. Zero touch, totally automated process. Okay, let's look at what we are going to work with. Our input is going to be a list of 3D points in which a filled voxel exists. What we want to get is a mesh, or a 3D model that Unity3d can understand and display. To design my voxel models, I'll use a free software called Voxel. In this video, I'll skip the process of unpacking the data from Voxel's files, but let me know in the comments if that's something you're interested to understand. Alright, this is the end result. We select a file in Unity and we click import, and we get the raw mesh. No colors yet, but the shapes are all there. Let's look how this is done. If you have seen the original video about the previous library, you'll remember how complex and how long the code was, only to achieve so little. It had long utility classes, dozens of misnamed subtypes that reused the same name for a different purpose, and well, it had hundreds of methods. I wanted to have something clean that I can extend with my automation without the fear of drowning in the ocean of code, and I wanted to be smart about triangulation. This is the process that breaks up the polygon into a set of triangles that GPU can understand. Right, this is a good moment to discuss what we want to get at the end of this process. Basic mesh is composed of two arrays, a list of 3D points called vertices and a list representing triangles. These triangles are represented by 3 integers containing indexes of vertices from previous first array. This is done like that because we are likely to reuse the same vertex when we describe triangles for it, and vertices are bigger in memory than simple index. Let's look at this drawing I've made. We'll simplify things to 2D because it's easier to read, but the rules are the same. We have a mesh which has 6 triangles, and many vertices are reused. Obviously, we can see that vertex number 3 is used in almost all triangles, but also each of the edge vertices is used in at least 2 other triangles. If we assume that every number is the same size, to represent vertices we need 2 numbers, and to represent triangles we need 3 numbers. Total here is 12 numbers for vertex list and 18 for list of triangles, so total of 30. If we were to repeat the full coordinates of vertex for each triangle, we would have 36 numbers already. If those numbers would be 3D coordinates, this would be 54 numbers, 6 triangles times 3 vertices times 3 coordinates. And the difference gets much bigger when we have a real mesh with thousands of triangles. This is why we have to come up with separate lists of vertices and triangles. Ah, I see that you like my dot patterned paper. This is my coding trick you should steal. I use a lot of paper to help my thinking and analysis of the problems. People do this on whiteboards or in notepads, but I think it's best to think when your paper has a pattern that is right for the problem at hand. So I'm printing whatever seems to be working best. You should do the same. Okay, enough theory. Let's look at the code. I wrote a voxel mesh class that has public constructor and public accessor to Unity3d mesh. Everything else is private. As I want to keep the process very streamlined, we have 5 private methods and 1 type alias, mesh piece, and that's all. So pay attention to this alias. This is a fragment of previously discussed output, a smaller part of the mesh, a set of triangles that make up 1 polygon. It could be, for example, front face of the cube. Let's look at the constructor. It calls each step of triangulation and also calculates where is the center of the object. This is necessary to compute how each side of the object connects nicely to the other sides. We'll get to that. Magica Voxel file loader gives us a dictionary of voxel position mapped to color ID. We disregard color for now, but we are greatly interested in the positions. Let's start processing. First step is to figure out which faces of each voxel will be visible. Think of it this way. All voxels have all faces visible if they are separated from each other. But when we touch one another with faces, those faces that make connections are not visible anymore and thus not needed. We will try to remove as much information as we can at this point. So what do we do here? We create a dictionary for visible faces. We'll map voxel position to a byte, where each bit will contain information if one face is visible. Bit 0 for front face, first for back, second for left, and so on. We iterate through all of the voxels and all directions. We check if there is a neighbor there. If there isn't, the face is visible. And we do bitwise OR operation that sets this bit responsible for direction to true. If at least one face is visible, we store this voxel in our dictionary. Nice and easy. Ha! You see how I used helper direction class here? This is a nifty little thing I wrote. If you ever think about utility classes, do it this way. Direction is an actual class, but it acts like an enum. I've made a constructor private, so only this class can create instances of direction. And it represents all 6 orthogonal directions, or axes of the world. This class contains a static list of all directions, and each direction has few operators. It can implicitly become a vector, and each instance knows its index in the static list. Super convenient and helps to avoid writing any magic numbers or repeating code for different direction. Okay, enough of this. Let's get back to voxel mesh. And by the way, if you think this idea is cool or you learned something, write a comment or leave a thumbs up. Cool, so this is how I am able to figure out where neighbors are and get indexes from directions. Let's move on to the next step. Now I want to get slices or layers of faces that are on the same plane. Thanks to that, I'll be able to create polygons, and that will be used in triangulation. Of course, we will start by creating a storage for our output. We'll have an array with one entry for each direction. These entries will be dictionaries that map depth of the slice to set of 2D points that represents visible faces of this layer. I know this may sound confusing, so let's look at this picture and compare what is represented by which piece of code. As a side note, I find it kinda annoying that you cannot specify names for key and value of dictionary. I could explain things so much better. Cool, so for each direction we need to fetch visible faces and put them in this set. I want to do it in a uniform way, so each layer is represented with Z coordinate for depth and X and Y specifying the face position in the layer. And it shouldn't matter which direction it is. I can then write an algorithm to extract polygons without caring if I am processing top, right or front of the model. To do it, I will need to calculate rotation of the face to uniform position front. So all of the faces are being mapped from here to here, from here to here and so on, everything mapped to front. Again, I will use my direction class here. For each direction I have a quaternion, which represents the rotation of this face in relation to front. Since I'm doing the opposite, reversing the face to front, I will use inverted version of the quaternion. Now, for each visible face of the voxel, I can check if appropriate direction bit is set. To make it uniform across all faces, I translate the vector so the center of all voxels becomes point of origin, or 0. Now I can perform the rotation with the quaternion and restore the vector to original position again. I store this value in a slice and that's it. Seems easy enough, but believe me, finding the right way to do it took quite some time. Something always was off. Eventually I pinpointed my issues to not calculating the center correctly. I was using a constant point, but it works best if center is averaged and rounded to int. Okay, if you thought that code before was complex, brace yourself, cause now the real fun begins. We'll create tessellated mesh pieces, or make lists of vertices and indices for every polygon we can make from the faces on slice. Again, create a container array of lists of pieces, one list for each direction. For every slice in that direction, we'll convert it to polygons and convert those polygons into a contour. Contour is exactly the same thing, but it belongs to Tessellation library, libtest.net. I've decided I don't need my own implementation for this functionality just yet. I asked the library to break the polygons into triangles. But hold up, how did we get those polygons? This is an important question. Of course, I called to a private function that I want to show you now, slice to polygons. If you ever encountered a term dynamic programming, this is what I'll do here. It stands for breaking up complex problems into sub-steps, which will give you partial solutions stored in memory. Those can be later used for full solution. Here we go. Let's start by finding all the edges that are 1 unit long. Let's draw again. I want to create a map of points that are on the edge of our polygon. But there can be two special cases where point can be intersected by an edge, so I need to create a dictionary of lists to handle these. Think of it as a collection of small arrows that have point where they start, this is our key, and the direction in which they are going. To come up with a full map of these guys, we'll go through all of the faces we have, and for each of them we will apply all the rules I externalized into this list. I like to code like this. I feel like putting such things in the code of algorithm is making it cluttered. If I can abstract the behavior away from the algorithm, I'll do so. So what do the rules say? Well, they basically state that if there is no neighbor in that direction, then there should be a segment or an arrow starting at origin and going counterclockwise from that direction. Okay, so why counterclockwise? Well, if we come up with this rule that all of the polygons have these edges counterclockwise, and all of the holes in those polygons are clockwise, this allows tessellation to come up with triangles that don't cover things that are recessed in a shape. Now, for the last part of the process, extracting polygon paths. So, what is path here? Well, it should be a list of points that make a polygon, but the smallest list possible. So we don't take points that don't add any information to the shape. Also, if more than one polygon is on a slice, we need to extract their points into a separate list. Sounds hard, but it's doable. So how can we do this? While we have any points in our map, I will pick up a point and see in which direction it is going. Then I will move there and see if there is another point in that spot. If that's the case, I will extract it, and if it has different direction than previous, it means I have hit a corner. So I'll take that point into my polygon. I will continue to do so until I will run out of points. Now, to handle those special cases I've talked about before. If we have a case where at one point we have segments going two different directions, I always need to follow counterclockwise direction if possible. So I'm going to look it up in my dictionary, and if I find there is matching segment, I will use it. Otherwise, I will just take what's available. This will give me all the polygons that exist on this slice. Sweet. Okay, quick reminder. We have taken those polygons and tessellated them. Now we have lots of lists of triangles. And as final step, we need to merge those small lists into a bigger one. And that is what generate mesh does. These loops iterate over all of the collected triangles and make it so they are now indexed within one space. I can't just simply append because unrelated polygons are all indexed from 0, so they would point to the wrong vertices. If you remember the previous video on Poor library, they invented something called unlimited mesh, to store meshes that are too big to fit in 16-bit index. I am replacing their entire class to manage this with those two lines. First I check if there are more indexes than we can fit in 16 bits, and if that's the case, I switch to 32-bit indexing. However, I doubt that my optimized tessellation would even exhaust the first space we have available. But hey, now it can. One last important step is to translate the dictionary of vertices to actual array that can be used by Unity3d. I could simply call .toArray on dictionary, and there is high chance it would work. But there are no guarantees that vertices would be returned in order of insertion, and we are screwed. To avoid this, I'll iterate through vertices and update the vertices array at index retrieved from dictionary. Done! We are producing the tessellated model that Unity can now parse and understand. This was a lot of work, but still a lot of fun. I need this for my automated rigging. I want to automatically detect where the bones should be and rig the vertices of appropriate body parts. Something like this. I'll make a video about that soon enough, but first, maybe I should look into adding colors to my character. I think UV maps should be my next project. Meanwhile, let me know how you would improve this code or what part you enjoyed the most. Subscribe, I'm gonna see you in the next one. Cheers!